Okay, everyone, this is the part 3 of the mechanics section, and today we have the second chapter, periodic motion. And this video, we are going to complete everything of this chapter except the short questions and numericals. So before we start off, we need to have basic understanding on what is periodic motion, and we need to mainly know about the simple harmonic motion, which is also called SHM. So let's start this and let's go thoroughly through every single topic. So first of all, we need to define what is periodic motion. So as its name suggests, periodic motion is the motion in which the position of particles gets repeated after certain or equal interval of time. For some, for an example, the example is a motion of simple pendulum. So let me write the definition. Periodic motion is the motion where the position of a particle undergoing this repeats after equal interval of time. And the example is the pendulum, motion of a pendulum. Now the next topic, just like periodic motion, is oscillatory motion. Oscillatory motion. This is also called vibrating motion. So what does this mean? It is defined as the same thing but in to and fro motion. If the particle moves to and fro motion from about a fixed point which repeats after a certain interval of time, then the motion is said to be oscillatory motion. For example, let me write it. Is it visible though? If it is. If the particle moves to and fro motion about a fixed point which repeats after certain interval of time, then the motion is called oscillatory motion. We need to also understand the relationship between periodic motion and oscillatory motion, as all the oscillatory motion are periodic in nature. However, all periodic motion may not be oscillatory. This is a thing that might be asked to you in MCQ. Other than that, there is nothing that can be so potential of asking in the exam out of this much. This is for a basic understanding. Now we are moving on to something that is frequently asked in your examination. So now it's called simple harmonic motion. Simple harmonic motion. This is a very important thing. You must understand this. So to define simple harmonic motion, you need to understand what is oscillatory motion. The definition of simple harmonic motion goes as: if the particle moves to and fro motion about a fixed point along the straight line which repeats after equal interval of time, that much is just oscillatory motion, and then such that its acceleration is directly proportional to the displacement from the position towards the mean position. So let me tell you once again. Simple harmonic motion is just oscillatory motion where the acceleration of the particle is directly proportional to the displacement from mean position and towards the mean position. Let's imagine there is something that is going on oscillatory motion just like this, where this is its mean position, this is the mean position, and these are the extreme positions. So what does it say is that in oscillatory motion the particle is okay, now you can see it. In oscillatory motion the particle A is going through this in normal manner, in like periodic manner, to and fro. It goes here and come back, goes here, come back. But for this to be simple harmonic, what should happen is the acceleration through which this thing moves should be directly proportional to displacement. That means from the mean position, the more it moves towards the extreme position, that means the displacement, let this be y first for a minute, while the y increases, the acceleration must increase as well. That means the particle has more acceleration at this point compared to this point and towards the direction of mean position. In any case, the acceleration should be towards the mean position. That means this should always try to fall behind, and with acceleration increasing with displacement. Okay, if you understood that, crazy nice, but if you did not, it's okay because you will understand it eventually. So now let's write definition. If the particle, you can just write this and then add something in the end. If the particle moves to and fro, motion about a fixed point which repeats after certain interval of time, okay, yeah, fixed point, you need to add one thing here, fixed point along a straight line. If the particle moves to and fro motion about a fixed point along a straight line which repeats after a certain interval of time such that the acceleration of the particle is directly proportional to the displacement from mean position and towards the mean position. This, as you can see, is the mathematical definition of simple harmonic motion, where acceleration is directly proportional to the displacement. Now we're moving on towards the equation of simple harmonic motion, and to do that we need to first understand what is simple harmonic motion and how does that actually work. So first of all, wait a minute, you need a circle to demonstrate simple harmonic motion. If we consider a particle having mass m, let this be a particle having mass m rotating in this circular orbit. It is rotating in this circular orbit, and the radius of circular orbit, the center is this, let it be O, and the radius is r. Let's divide it into 4 quadrants, or four what it is called, semispheres, I think, semicircles, or I don't know. Yeah, there are 4 of these, and let the displacement, angular displacement covered by it from here to here be theta, just like that. And if you do this, this is the distance x, which is, and here it is the distance y, the distance, resolved distance. Let the particle be p, and after that what we need to do is calculate the angular velocity of the particle along with the theta the displacement of the particle. So we need to resolve it, and then we can find the displacement of the particle, and after that we can basically find the velocity of particle, acceleration of particle, and there is an important derivation in that thing. So let's derive the equation of simple harmonic motion just right now. Then we go velocity of particle in SHM. Yes sir, yes sir. Oh yes, velocity and acceleration. Yeah. Okay. So we need to write some language right here. Let's consider. You can see this. Let's consider a particle. You can just write everything here. Consider a particle having mass m is rotating in a circle of radius r with angular velocity omega at any time t. At any time t, the particle is at point. The particle is at point P with a angular displacement theta. You just explain the figure here. It's not necessary you use my words. You can just do that. Now we know that omega is theta by t, displacement by time taken is velocity, right? Similarly, so this gives that theta is equal to omega t. That means displacement is velocity into time. So from figure we know that sine theta. How does this happen? Let me tell you. Just take this much for some time, this much, and then like this. Here is the theta. This is, if this is P for here, if this is P, this will be P cos theta, and this here will be P sin theta. That is basic vector resolving. You know that, right? So if that happens, then we know that from figure we need to keep it. Sin theta is equal to, in this triangle, in this right angle triangle, this is a right angle by the way, sin theta will be equal to perpendicular by base, that is this thing by base. This thing is equal to y, this is equal to this, so this is equal to y, this thing is equal to y, and base perpendicular by p by h, hypotenuse is this, and this is basically the, what is it, the radius of the circle. It is the radius of circle. So sin theta is equal to p is perpendicular, that is y, and base is r. Or it is basically r sin theta equal to y. You can do it this way, it is the beginner's way, but you can simply write from figure, since this is p sin theta, then we know that p sin theta this is equal to this, so you can just do r sin theta equal to y. You can do anything, just find this much, just choose this method. It is simpler and easier. Now from equation 1, this is the equation 1. From equation 1 we have r sin omega t equal to y. So this is the equation of a simple harmonic motion. This gives the displacement. This gives the displacement of a particle executing SHM. Motion of particle along the circular orbit is not SHM, but its projectile along the diameter gives displacement of particle. And by the way, this is not a circular, the particle is actually in circular motion. It is not actually in circular motion. It is like executing SHM, but what happens basically is, if you look at a circle, that is, if you look at a SHM, this is a SHM graph, by the way. SHM is basically sine graph from this figure, as you can see. So in, if you look at this graph from a different perspective, if you rotate this graph like this, you will look at something like this. It will look something like this from a distance away. So we basically use the R here means the amplitude of this graph. How do I know that? Because this looks like a circle when the graph is rotated. I cannot show you in 3 dimensions, but you have to understand that this is the radius of the graph. If I remember while editing, I can add the thing I'm trying to explain here, that sine graph when looked from this side, from the x-axis, looks like a circle, which can then be like educated or taught as a circular property, and this acts as the radius, which is this thing. The radius is the amplitude of the sinusoidal graph. So therefore the motion of particle along the circular orbit is not SHM, but its projectile along the diameter gives displacement of particle in SHM. Now we're moving to velocity of particle in SHM, then acceleration of particle in SHM, and then we are going to where are we going? We're going. So displacement of particle executing SHM is, again, we are also doing a sample question then. Okay, I don't think I have to do anything here. This is the easiest thing you'll ever see. Velocity of a particle in SHM and acceleration of a particle in SHM. Okay, how do we do these? We know we already have the displacement graph. This gives the displacement. So if we differentiate it in with respect to t, we get the velocity. That's it. Differentiating with respect to t, dy by dt equal to rd sine omega t by dt. This will give us, this will be velocity, velocity will be equal to r, and this will be, if you use the chain rule, d sine omega t by d omega t into d omega t by dt. This will be v equal to r omega cos omega t. This is the equation of velocity, but it is not written in this format. It is changed to v equal to r omega, and cos omega t changed to 1 minus sine square omega t, and sine square omega t basically is the value of y. We know that very well. Do we not know that? We do know that. So what happens is, it goes here, I have to write it here, understand it again. So it will be v equal to r goes inside, and it will be omega times r square minus r square sine square omega t. The r went inside, that's it. V equal to omega, and this will be r minus this is from equation 1, this is from this equation, the one equation, this is y, so r square minus y square, and this is the equation of velocity, the velocity of particle in SHM. This is the equation. So at mean position, this is the mean position. This is the mean position. It goes up here, and then it's basically we are showing the motion of the particle. Look at this. The particle is in mean position here. It goes right here and comes back here. But in circle, we're showing it like there. So that's how it works. This is the one cycle, and these are the 4 cycles represented by a circle. So that's what happens. So yeah, while the particles goes from here and comes back here, the mean position, the value of y here is 0. It is a mean position. In the extreme position, the value of y will be maximum, or the value of y will just be y. So well, there are two cases. Case 1, while y equal to 0 at mean position, v will be equal to omega under root r minus 0, that will be omega r. This is the velocity at mean position, and this is the maximum velocity. That means the velocity of the particle in SHM is maximum in the mean position. We get it, right? In a pendulum that is moving in SHM like this, there are the 3 points, the mean, 2 extremes and the 1 mean. The maximum velocity is right here. That means the minimum velocities are right in these 2 points. You can just simply imagine this, or you can make a mind makeup. We have now case 2, while y equal to y, that is at extreme position. This is v will be equal to omega r square minus y square, simply y square. And but we need to know that at extreme position, the extremist position is this is the extreme position. Here y will be equal to r. That is what we need to understand. Not in this figure. In this figure, y might not be always equal to r in this figure. But when you imagine it, the radius is equal to the maximum amplitude. Or it is always, oh my god, it's always equal. Look at this. It is always equal. The y is equal to r. So you just put y equal to r. You put r here, my bad. Okay. Y equal to r. So it will be v equal to omega r square minus r square equal to 0. This is 0. And this is the minimum velocity. That means at this point, the extreme point, the velocity of a particle in SHM is 0. Just like that. Now for the acceleration. Acceleration of the particle executing SHM. Okay. What do we have is velocity v is r omega under root r square minus y square. Omega r square minus y square. This is the equation of velocity of the thing. But we cannot differentiate this and get a fruitful result, because acceleration is to be determined by differentiating this equation. V equal to r omega cos omega t. And where did this come from? Right here. I told you earlier. We need to know this as well. V equal to r omega cos omega t. And when you differentiate this, what happens is differentiating both sides with respect to t, dv by dt will be equal to dr omega cos omega t by dt. Now since our r omega cannot quite be differentiated, so we are going to just differentiate the cos portion. Dv by dt equal to r omega d cos omega t by d omega t into dt d omega t by dt. Simple chain rule. I think everybody knows what's happening. Dv by dt equal to r omega minus sine omega t, or this is acceleration. That will be equal to this will be equal to minus r omega sine omega t. Now again we need to put r sine omega t as y, so we put them together. A equal to minus omega r sine omega t, and we know that from the earlier equation right here y is equal to r sine omega t. So A is equal to minus omega y. That is how, oh wait, we made a mistake. Look at this. Here is r omega itself, r omega, then its derivative will be omega. So it will be times omega times omega times omega. This will be omega square y. That is the equation for the acceleration of a particle executing SHM. So there are two cases as well here as well. Case I, at mean position. At mean position, what is going to happen is the displacement will be 0. So A will be equal to minus omega square. And this omega with y equal to 0, A will be also be equal to 0. This is called minimum acceleration. Look at this again. At right here, there is maximum velocity but zero acceleration. Why? Because it is straightly and there is no gravity acting against it. But when it goes here, there is gravity pulling it back. Also, there is restoring force pulling it back. Similar in this area, it's gravity plus restoring force pulling it back. So here there is no gravity and no restoring force. It is in maximum velocity but nil acceleration. You need to understand that much. We have 0 in minimum, and now at case 2 we have at extreme position. As I said, y will be equal to r. You can just take the magnitude, or you can just do plus or minus r, and this will be equal to a is equal to plus or minus omega square r. So this is the maximum value. You can just say a is equal to omega square r, or a is equal to minus omega square r, depending upon the direction, and it does not really matter about the sign. You just need to remember omega square r is the maximum acceleration of a particle executing SHM. All right. Then there is a quick question for you all. You can do this question. I'm not going to do this question. You can just check yourself, your understanding. The displacement of particle executing SHM is y equal to r cos omega t plus phi. Let me write it here. Is y equal to r cos omega t plus phi. With the displacement, you need to calculate its acceleration. Calculate its acceleration. Let me give you some hint. Differentiate that 2 times, and that's it. That's all you need to do. You will find the acceleration if you differentiate this equation 2 times. Do it yourself to check your understanding. Now we are going to variation of displacement, velocity and acceleration with time. So let's go. There are 5 segments of time during what is it called, simple harmonic motion. We are assuming this is our pendulum, and the whole time taken by this is t. If you start from this point, it goes all the way to this point and comes back here, it takes t. So that means to come up to here, it takes t by 2, half time, and then to come up to just here, it takes t by 4. So t by 4 is the smallest fraction of time we can study, and it is here it equal to t equal to 0. So if you don't understand, let me tell you once again. Here t is equal to 0. While the particle goes through up to here, the t will be equal to t by 4. And when it goes up to here, t will be equal to t by 2. When it comes back here, t will be equal to or 3t by 4, because it goes here and comes here back. And when it goes up here again, it will be t equal to t, or it completes itself. So that is a t. So now at t equal to 0, we have, or let's keep this small t, at time equal to 0, we have y will be equal to r sine 0. Omega t is 0. That will be 0. That means displacement is 0. Here the displacement covered is 0. The velocity is given by r omega cos omega t. This will be cos 0 into r omega, and this is 1, and that's r omega. This is the maximum velocity. Here displacement is 0, acceleration is 0, but the velocity is maximum. This is the first case. At the second place, there is at t equal to t by 4. We are here now. At this point, the displacement is r sine. What is the displacement right here? The displacement here, the whole displacement, we need to understand this. The whole displacement is, we have omega t, right? So omega, what is omega? We know the omega is 2 pi by t. That is the formula of omega. And t is t by 4. So t by 4. This cuts off, this cuts off. So it will be pi by 2 equal to r sine pi by 2. Is it not? Yes, is it? It is. And what is pi by 2? 91. That is r. So the displacement here, this, while the particle comes here, the displacement is this radius, as I told you earlier. So r, and the velocity is r cos, we can just write pi by 2 right now, right? R omega, omega r cos pi by 2. This will be cos 0, so 0. The velocity here is 0. Acceleration, again, we know that acceleration is minus omega square y. So y here is r, as you can see. Or is it r? Y is equal to r. So since y is equal to r, this will be minus omega square r. This is also maximum acceleration. Oh, sorry. It is not maximum acceleration. This is somewhat acceleration. This is not the maximum acceleration, but it is somewhat acceleration. Oh, wait a minute. I forgot the a here. The acceleration here is 0, by the way. At t equal to 0. At this point, oh shoot, there is no acceleration in this point. Oh yeah, the mean position is this one. I'm so sorry, the guys. Yeah, we have assumed this as the mean position right here. So at t equal to 0, I'm just doing it from my notes, and in my notes the mean position was assumed right here. So at t equal to 0, we need to redo this. At the t equal to 0, at t equal to 0, look at this. At t equal to 0, the value of displacement is 0. There is no displacement. But velocity here, in this point, at the mean position, the velocity is maximum. But there is no acceleration. I told this earlier. I'm pretty sure you have already corrected it yourself. But still, yeah, that's how it works. And this is the maximum acceleration in, this is the point. Okay, let me just do this again. Let me just draw this figure again. This is the t equal to 0. This is the t equal to 1 by 2. This is t equal to, goes here and then goes here, right? So while it goes here, it's t 1 by 2, and it's come back here. So this is 1 by 2 plus 1 by 2. This is t equal to 1. T equal to 1 is also right here, and here is t equal to 3 by 2. So that's how it happens. And at t equal to t by 4 is this. Now we go to at t equal to t by 2. You all know what to do now. Equal to r sine omega is 2 pi by t, and into omega into t, small t is t by 2. You can cut this, and this is pi. Sine pi is how much is sine pi? Sine 180. I think it's 0 as a 1. Sine 180 is 0. So it is 0, and we know that when the at t equal to t by 2, at here displacement is 0, which is not correct. So we are missing something. At t equal to t by 2, how can displacement be 0? Displacement cannot be 0 at that point. Oh, this is t by 1 by 4, and this is 1 by 4 plus 1 by 4. This is 1 by 2, and this is 3t by 4. 3t by 4, and this is, yeah. So at 1 by 4 it is 0. At 1 by 2, however, it is 0 again. At 1 by 4, look at this. At this point, at 1 by 4 is this point. It's r, the radius. At 1 by 2 again, at this point again, it is 0. So when it is 0, acceleration is maximum, that is omega square r. And no, when y equal to 0, this automatically becomes 0. When displacement is 0, y automatically becomes 0 and velocity becomes maximum. So now we go to t equal to 3t by 4. That will be y equal to minus r and v equal to 0 and a equal to minus omega square r. At t equal to t, we know that t equal to t is the mean position again, so that is y equal to 0, v equal to maximum, that is what is the maximum value of b, omega r, and a is equal to 0 again. That is how it works. This is very, I did it in a hurry because it's very easy. So you can see how this happened is, the formula for this is r sine omega t, and minus 1 is the value of sine 3t by 4 omega sine 2 pi by t into 3t by 4. When you cut this and this, sine 3 by 2 pi is minus 1, and this happens, and similarly this also occurs. So now that we have all of them, we are now moving to the next topic, that is energy in SHM. What are we moving to? We are moving to energy in SHM. Alright then, we need to derive the equation for the total energies, the sum of kinetic energies and potential energies in simple harmonic motion. After that, we have simple pendulum and the vibration of mass in a vertical spring. And after that, we got angular SHM, and then the chapter ends. So we have 3 derivations after this. Okay. Energy in SHM. The total energy in the SHM is the sum of kinetic and potential energy. So the total energy in SHM is the sum of potential and kinetic energy. Sum of potential and kinetic energy. The kinetic energy is due to the motion of the particle, whereas the potential energy is due to the restoring force, that acts on the particle. So let's start with kinetic energy. First we have kinetic energy. We have the velocity is given as, for simple harmonic motion, omega under root r square minus y square. This is the equation of velocity. Then we have kinetic energy equal to 1 by 2 mv square. It will be 1 by 2 m omega under root r square, m omega under root r square minus y square. This is the equation for kinetic energy. And for potential energy, now for potential energy, we need to find out the potential energy by the formula of restoring force, because restoring force acts as the potential energy here, the work done by the restoring force. So firstly we need to calculate the acceleration. We know the acceleration is equal to omega square y. This is the acceleration. Then the restoring force is F equal to ma equal to m omega square y minus m omega square y is the restoring force. So after that, we now have to integrate. We now have to find the work done. So first of all, now we start with a small amount of work done to displace the particle through displacement dy against restoring force is. Now we write dw equal to f dy minus f dy. And why are we doing this? Because restoring force, because the work done is defined as force times displacement, and the force is negative because it is restoring force and is in the opposite direction of the displacement, so that's why it's negative. Now in this equation, what we need to do, wait a second, what we need to do is we need to basically integrate. We need to first put the value of f, then integrate. We know that f, we just found out, is the minus, it's first minus, and then the f is minus m omega square r. This is the value of r. I mean, is it r or y? Let me see. What is f? Okay, it's y. Look at there, the force, it is y. So we are putting y, omega square y minus, times dy. Now we can simply simplify this as m omega square y dy. Now we make this equation 2 or star, and to find the potential energy, or which is just the work done by the restoring force, we can simply integrate this equation from 0 to r, 0 to y displacement, sorry, it's y, yeah. It might not always be r is a special case, so we're just going for y. That is, this side will be y, and while integrating m omega square y dy, everything is not integratable, so it is m omega square y square by 2 and 0 to y, and that will just be omega equal to 1 by 2 and m omega square y. So this is the y square, sorry, this is the equation, which is the potential energy stored in the particle. Therefore PE, potential energy, is equal to 1 by 2 m omega square y square. So now the total energy TE is given as KE plus PE. So KE plus PE will be equal to, KE we derived earlier is m 1 by 2 m omega square. Where is it? Look at this, 1 by 2 m omega r square, m omega under root, is it visible? Under root r square minus y square plus 1 by 2 m omega square y square. You can take 1 by 2 m omega common, and what remains is under root r square minus omega square plus y square is what remains in common. And so I think that much is it. Where is the equation of mv square. We made a mistake earlier. Look at this. This is mv square. mv square. So m is here, v is, this should be squared as well. So this is actual thing. So while squaring that, it changes right here as well. This will be the omega square, this will be omega square, and this will also be squared. So we can take squared common here, and what remains here is the square of this plus that. So this will be 1 by 2 m omega square, and this will be r square. This will both cut, so r square will remain, and that will be the total energy stored in a what is it? Total energy stored in a SHM, a particle executing SHM. Now there is a graph for the energy graph. So let me draw it for you all real quick. It is a very beautiful graph. The energy goes up here, and there is another line like this, straight line, and this is the point minus r, and this is the point r. So these two are in a straight line, by the way. I'm just not so good at drawing graphs. Yeah, that is the graph, and this is the energy. This is the origin, and the up one is the total energy. The total energy remains constant in every single part of the motion, whereas the potential energy is this one, and kinetic energy is this one. Look at this. This is the extreme position, the negative r. At the negative r, there is minimum kinetic energy. The motion is negligible, and the potential energy is maximum. Oh yeah, is not maximum, but it's somewhat very high. The potential energy is very high, and look at this. This is the mean position. At the mean position, the value of which one is this? Potential energy. At the mean position, the value of potential energy is at the mean position, the value of potential energy is 0, and the value of kinetic energy is maximum, or that is just total energy. However, at the extreme position, the potential energy, look at this, is maximum in these 2 points. These two are the extreme points, the radius, and the kinetic energy is 0. So this is the graph of and this is the displacement, by the way. This is the displacement. So this is the graph. Now we are moving on to the most important part of this chapter. The most important part, simple pendulum. Most important. This is the most important part of the chapter. You must never miss this part, and we are going to derive the equation for it, and the time taken, the time of the total time taken for the motion of the particle, and then we have the graphs of t square versus L and t versus L. So we are going to do that now. Okay, so first we start with defining it, and the question that is asked is prove that the displacement or the acceleration, or prove that the acceleration of the bob in simple pendulum is directly proportional to the acceleration. This is the question that is asked. A derivation for 3 marks. So first let's define a simple pendulum. Simple pendulum is a heavy mass suspended by a inextensible, massless, and flexible string from a fixed point. We can draw a figure regarding it. Let me draw it in the side like this. This is a fixed bar and this is a point S in the thing, and let this be the bob of pendulum, and you can see this is where it reaches after a certain time, and its motion is towards the center, towards this way. It tries to move towards this way, and the resultant tension, it goes like this, and the force, since it goes here, its mass goes directly downwards, that is mg, and the component of this force that goes here, there is the theta, and the angle is theta, so here is mg cos theta, which is neglected right now, and here is mg sine theta, which pulls it back towards the mean position. This angle is theta and the point is S, and let this be the tension on the wire or on the string. This also has mg going below. The displacement covered by this is y, and the position of it is from A to B, and that is all you need to do in this figure. So now we write some language in this. Okay, so let's start writing a language. Just write whatever you see in the figure. Consider a bob of pendulum having mass m is suspended from a fixed support S by the string of length L, and you need to know that the length is from the point S to center of gravity of the bob. Okay. When the pendulum is slightly displaced, by the displacement y, or no, displacement is theta. We cannot write displacement y, displacement theta. The displacement theta, this is y, so this is theta, on theta, the component, the y component, right, or just say the mg sine theta component of the weight of the bob brings it back towards the mean position. We know that much, right? Now then, it provides restoring force. It does provide restoring force to the bob. That is, restoring force is equal to minus mg sine theta. It is always negative, don't forget that. So this can be written as ma, and this will be equal to minus mg sine theta here in this. If this is very small, that it is straight line, so in this triangle this is the right angle, and to find the sine theta, we know that sine theta is perpendicular by base, so no, perpendicular by hypotenuse. So the formula will turn out to be AB is the perpendicular, this is the right angle, and this is the angle, so this is the perpendicular, and the hypotenuse is this perpendicular base, right? So yeah, the hypotenuse is this is the hypotenuse, and this is the base. So mg sine theta is hypotenuse by base, right? So hypotenuse is wait, what is sine theta? Sine theta is perpendicular by hypotenuse, so perpendicular is AB, and hypotenuse is BS, or you can cut the m. A equal to minus g. AB, what is AB? Do we know what is AB? We do. AB is y, and BS is L. So A will be equal to, write the constants in one side. A will be equal to, G is a constant, L is a constant, and Y is only that's different. So what we have now is A is directly proportional to Y. So this is equation 1, let this be equation 1. So we have this. Hence its motion is SHM. How do we know this? Because from the definition of SHM, we knew that this should happen in the SHM. Earlier we wrote the definition of SHM. Just right here. Look at this. Acceleration is displacement. This must happen for SHM to happen. So yeah, that happened right there, as you can see. So it is SHM. This much might be asked for in your exam, but it can again ask you the time period. So again what we need to do is, for SHM, we know that acceleration is minus omega square r. We just did that earlier. Oh, I mean y. This is the maximum case for r, y, and this is the equation 2. If you compare 1 and 2, you will find out that comparing 1 and 2, you can equate them. Minus g by L times y is equal to minus omega square y. This will cut, the both y will go, and you can change, to find the time period, you can just change the omega square to omega is 2 pi by t. So this can be written as, to find out t, we can just, and this is square by the way, t equal to under root, this goes here, and these shift there, so it will be 2 pi will be outside the root, and this will be L by g. This is the equation for time period of the. Okay, now as you can see, the next topic is vibration vibration of mass in a vertical spring, and I have drawn three springs which are the same springs. This is a spring with spring constant k, and when a mass of weight mg is suspended in the spring, it displaces a bit downward with a displacement of L, and when it is pulled back with another force, just like this, when it is pulled back, then there is a force F2 applied downwards, and then it comes more down than the initial position, and the displacement is y. What is happening here is, you are keeping a spring, and then a spring is put, and there is a mass, so the mass brings the spring a bit down, and when you pull and leave it, the spring goes on up and down, up and down. We have to prove that the motion of that up and down spring is simple harmonic in nature. we know that to prove the motion simple harmonic, we basically have to prove that the acceleration is directly proportional to the displacement. So first let's write some language. This is a consider let's say a spring having force constant. I'm sorry, that's a force constant. Okay, consider a spring having force constant K is attached to a rigid in the figure. When a block of mass M is attached to one end of the spring one end of the spring is stretched by displacement. The spring is stretched by displacement L. This L, it is down right here. Displacement L due to the force of weight, that is force of weight, the restoring force. The restoring force is F is directly proportional to L. Why does this happen? F1, sorry. Because if this length is very small, the force will also be smaller. That's just basic common sense. So that, and is it visible? Okay. After that, we put the constant, spring constant or the force constant KL here, and we always need to remember that this will be negative because the direction of force and the weight is opposite in direction, since it is a restoring force. Let this be the equation 1. Now the mass is now further displaced downward through displacement y by application of force F2. F2 force is applied so that the displacement y is covered by the spring, force F2. Then the restoring force now is the sum of both L and Y. So F2 will be directly proportional to L plus Y. That is, F2 will be equal to minus K times L plus Y. This will be equation 2. Like that. You can see now. Now that it is done, we need to find the effective applied force. So to do that, the effective applied force is, let it be F equal to F2 minus F1. This will be equal to minus K. F2 is L plus Y, and minus this is minus K L. So this will be K minus KL minus KY plus KL. So this will be cut, and this can be written as MA, and MA will be equal to minus KY. So if M goes the other side, A is equal to minus K by M Y. Since K by M is a constant quantity, let it be equation 3, and since K by M is a constant quantity, we can write that A is directly proportional to Y. So hence it undergoes SHM. That's it. Now, similar to what we did earlier, we need to find the time period. For time period, the acceleration in of a body in SHM is given by this formula. So this let be 4, and let's comparing 3 and 4, we obtain minus k by m y equal to minus omega square y. We can call the minus and y, and k by m equal to omega square, or k by m equal to 4 pi square by t square. This becomes t equal to 2 pi under root m by k. This is the expression for time period of a spring that is vibrating in simple harmonic motion. Now we are moving to the end of the video, and this is the last portion of this video. The last portion is called angular SHM, and we are going to find the values of find the expressions for angular SHM. So let's start. Angular SHM. Under angular SHM, first of all, the definition of it comes first. So angular SHM is defined as the oscillation in which restoring torque in angular anything, force is replaced by torque. So we say the oscillation in which restoring torque is directly proportional to angular displacement from mean position and towards the mean position is called. Okay, so let's remember the past. In SHM, we defined what we defined. First of all, we defined the SHM. First, we defined oscillatory motion, right? We defined oscillatory motion. Where is it? Here it is, periodic motion. Look at this. In this periodic motion section, we have here, we define oscillation. Look at this, oscillatory motion. If a particle moves to and fro motion about a fixed point which repeats after a certain interval of time, the motion is called oscillatory motion. We know that, right? And then if the particle moves to and fro in motion along a straight line about a fixed point, which repeats after a certain interval of time, such that the acceleration of the particle is directly proportional to the displacement from the mean position and towards the mean position. This basically can also be defined as simple harmonic motion is the oscillatory motion where the acceleration of the particle is directly proportional to the displacement from the mean position and towards the mean position. It can be defined in that way as well. Similarly, here we are defining it, the oscillation in which we are starting directly from the oscillation in which restoring torque is directly proportional to the angular displacement from mean position and towards the mean position is called angular SHM. I hope it's visible. Okay, now what does this basically imply is that torque tau is directly proportional to displacement theta, just like what happened in force F, restoring force directly proportional to alpha. But we did not write that, right? We wrote A displacement is y here. We wrote A because MA, but M is a constant, so yeah, just forget it. Similarly, torque will be constant, directly proportional to that, and we just write tau is equal to minus c theta, where c is torsion constant. Let this be equation 1, no confusions. Now let's consider. Now we know that the definition of angular SHM. We consider a disk, or wait a minute. We consider a disk suspended from fixed support is twisted by angle or displacement theta. I and alpha be the moment of inertia and angular acceleration. Then we know that tau, force, equal to mass into acceleration, right? But here will be I into alpha. So this will be equation 2, and from 1 and 2 we have I alpha is equal to, what was the last, minus c theta, right? Minus c theta. So let's find out alpha, that is minus c by I times theta, and we have here, this is a constant, so or alpha, okay, alpha, let's write it like this, is directly proportional to theta. That is just like A directly proportional to S, it is alpha directly proportional to that. So its motion is in SHM. This is the equation of angular SHM. Again, now we know that alpha for time period, what we can do is alpha will be equal to minus omega is omega and y is theta. This will be equation 3. This is a 3, this will be 4. Again, from equation 3 and 4, what can we conclude is minus c by I theta equal to minus omega square theta. This will get cut, this will get cut. So c by I equal to 2 pi by t squared, just like that. So t will be 2 pi under root I by c, Indian currency. You can remember it that way. This is the expression for time period of a particle oscillating in angular SHM, and this ends the topic. That is all the things except for short question and numerical that will be asked in your exam. Now we will do the short questions and numericals in the same video, in the next video. After that we are moving to next chapter, that is fluid statics. So thank you for watching your chapter.